Okay, guys, now we've finally gotten to the reason that we're doing all of this, which is to be able to predict what we need to do to change our dosing regimen when presented with drug and disease interactions. So when drugs and diseases cause problems with the pharmacokinetics of our drug, we want to be able to predict what we need to do to react. So that's what all of this has been about. So we're going to start with low extraction drugs. So low extraction drugs, remember, these are all drugs that are cleared by the liver. These are low extraction drugs where we know this is our rusty dairy, right? So the rate limiting step is the intrinsic clearance times fraction unbound. So the blood coming into the liver is going at a good rate, but the slowdown is actually in the intrinsic clearance and fraction unbound of the liver itself. So the rate limiting step is intrinsic clearance times fraction unbound. Therefore, our clearance is approximated by those two factors, intrinsic clearance and fraction unbound. And this also needed to be changed to our fraction that escapes first pass effect, which I used to symbolize it like this, but now I symbolize it as FH, is approximated by 1. Most of this drug gets through the liver, which makes sense, right? If it's a low E, low extraction ratio, we're going to have a high fraction that escapes that extraction by the liver. So we're going to use these assumptions to be able to figure out how to make changes as we have drug and disease interactions come along. There's no route dependence, no route dependence. Fraction that escapes first pass effect is approximated by 1, so we don't have any worries about whether it's given by IV or PO. It's going to be the same factors. So now what we're going to do is, if we give this drug IV, let's think about what's going to happen here. So we're going to give a low extraction IV, okay? So in order to figure out what's going to happen with that total concentration at steady state, we're going to say usually we just say our dose rate, but don't forget we have a salt form that might be a factor. And usually we think about our bioavailable dose rate, but we don't have to worry about bioavailability because bioavailability is going to be 1 since it's given intravenously. It's given right into the systemic circulation. So it's going to be S times dose rate all over, so drug in over drug out, as it always is. But knowing that our low extraction drug, the clearance is going to be equal to intrinsic clearance times fraction unbound, we can put that in here in our denominator because we know that clearance is dependent upon those two factors for this low extraction drug. So we can replace with just clearance and know that that's going to be determined by intrinsic clearance times fraction unbound. So now we know that our total concentration, if given IV for a low extraction drug, will be dependent upon our salt form, our dose rate, our intrinsic clearance, and our fraction unbound. So if there were a decrease in intrinsic clearance, that would cause a decrease in our clearance, which would increase our total concentration if given IV. So now you start to see the utility of this, right? Also, what if we have a drug that comes along and bounces our drug off its protein binding site? So we have an increase in fraction unbound. If there's an increase in fraction unbound, what's that going to do? That's going to increase our clearance, and therefore we're going to have a decrease in our total concentration if given IV for this low extraction drug. All right. We want to compare that then to our free concentration. Why? Because the free concentration is the active concentration. So this is what we measure. This is what comes back from the lab, but this is the active form, isn't it? So how do we go from our total? So this is our total concentration. Here's our total concentration. To get to our total, we multiply the whole thing times fraction unbound. Remember, we just determined that like 2 slides later, yes, before this, that C total times fraction unbound gives us C total times a fraction unbound gives us our free concentration, right? So that's what this is. So now we can say with a low extraction drug, our clearance is approximated by intrinsic clearance times fraction unbound. So what you should note here is that these two fraction unbounds will cancel as far as the equation goes. Well, what does that mean exactly? Well, what if we had this same issue where the fraction unbound is increased because of a displacement? Well, what you would say to me is, well, Dr. Earle, if you displace your drug from the plasma protein binding sites, that's going to increase your free concentration, isn't it? Well, yeah, initially you're going to bounce that drug off. So let's say you went from a fraction unbound of 10% or 0.1, and because of that drug interaction, your fraction unbound is increased to 0.2 or 20%. So your fraction unbound is increased. Well, of course, you're going to have a higher free concentration for a little bit until that free concentration, or until that drug gets to the liver. Because when the liver sees it, more of it's going to be free, right? So it went from only 10% being free to now 20% being free. So that additional free drug is available to be metabolized by the liver when it wasn't before. So that free fraction that is increased kind of peripherally that I think of will be caught up for once it gets to the liver. So that's why these two things cancel. And so your free concentration at steady state will not change. There'll be no change in your free concentration at steady state with this binding change. But what will the lab say? Well, the lab will show you that the free concentration is increased, and that's going to decrease our total concentration. So sure enough, the lab value may decrease. So if the lab value decreases, what's your team going to want to do? They're probably going to want to increase the dose rate, right? They're going to want to give more drug. Should they do that? No, because the free concentration, the active form, has not changed. If you increase the dose rate, you will increase the free concentration, possibly causing a toxicity situation. So this is really important to know, and really only pharmacists really understand this. And you may not feel like you understand it yet either. It's the first time you've heard it. But you do need to understand this, and we will be working with this. Okay, so what if we give, instead of it giving IV, we're going to give it orally? So oral administration versus IV for a low extraction drug is not a big deal because there is no route dependence, right? But let's go through it anyway. We know for a low extraction drug, the clearance is approximated by intrinsic clearance times fraction unbound, and that the fraction that escapes first pass effect is approximated by 1. So again, if we start by putting our drug in over drug out, we now, in this case, since it's being given PO, we have to worry about bioavailability, don't we? So we put in our terms for bioavailability. Bioavailability, as you remember, is determined by FA times FG times FH. So we put in here salt, bioavailability, and dose rate, so our drug in, over our drug out. What's our drug out for a low extraction drug? Well, it's intrinsic clearance times fraction unbound, isn't it? And what's our FH for a low extraction drug? 1. So we replace that FH with a 1, and we replace the clearance with intrinsic clearance times fraction unbound. And what do we see here? We see these are all the factors of determining our total concentration at steady state if given orally. Now, what about our free concentration if we give it orally? That's on our next slide, because it's too big to fit on one slide. No route dependence. All right. Now, what if we we're still giving it orally, but now we're talking about what's the free concentration. Well, once again, it's our low extraction drug. Whoopsie, why is this happening? A low extraction drug, our clearance is going to be dependent upon intrinsic clearance times fraction unbound. I guess you can't read that at all. And FH, or fraction that escapes first pass effect, is approximated by 1. So here's our bioavailability times salt form. So this is drug in over drug out times, in this case, we have to consider that fraction unbound because we're looking at free drug, aren't we? So if we go in and replace our clearance and our fraction that escapes first pass effect, we have salt form times FH times FG times 1, because that's going to stay constant. And our clearance is going to be equal to intrinsic clearance times fraction unbound. And once again, these fraction unbounds will cancel. So you can see again that there's really no route dependence dependent upon whether it's given IV or PO. All right, what about looking at half-life? Remember, I wanted you to consider half-life because half-life is how we determine if we want to make a change in our dosing interval. So we have our low extraction drug. What we know is that our clearance is approximated by intrinsic clearance times fraction unbound. So half-life we know is 0.693 times volume over clearance. And for a low extraction drug, we can replace our clearance with intrinsic clearance times fraction unbound. We can also replace our volume of distribution with the determinants of volume distribution, which are tissue volume times fraction unbound in plasma over fraction unbound in tissue. And what we can see here is that these two will cancel, right? So when there's a fraction unbound displacement here, it's going to increase clearance and increase volume, and those two things will also counteract each other. Does this make sense? Sure, because if we increase our fraction unbound, the volume of distribution is going to increase, isn't it? Because it can move out into the body now. And if our fraction unbound increases as far as clearance, more of it's available for clearance. So it increases our clearance and our volume to the same extent. So if there's an increase or a decrease in fraction unbound, you won't see a change in the half-life. Pretty cool, huh? All right. That's it for this, and then we'll come back and do high extraction drugs next, which are a little more complicated. So hold on to your hat.